Having considered the history of IoT, now we'll consider the topologies of IoT in terms of how it looks and how it's connected together. And we'll cover it in a few different forms. We'll cover it from a hardware form, how data is sent through the system, but we'll also cover it from a functional form of how things functionally connect and what jobs they actually have within our system. So this diagram here with our pyramid shows the hardware form of how data is sent throughout our system. And so we have our edge, and at the edge we have a whole series of devices, billions of devices in fact, and billions of new devices being added all the time. And those devices are things that are measuring everything from temperature and pressure and acceleration and various gases and chemicals and whatever they may be. There's plenty of them there. And so our edge senses all those things and then sends it up to the fog. And in the fog, we do a few things. One is we eventually route those signals to the cloud and to the internet, but we can also do data processing in the fog. And so we've got maybe millions of fog devices, which are things like, that include things like routers and gateways that allow our edge devices to eventually connect to the internet. So we've got that that's happening, but we've also got the processing happening. And there's two reasons why we have this processing happening. One is latency and one is processing power. In terms of latency, rather than sending data from the edge all the way up to the cloud and being processed in the cloud and then sending it all the way back down again, you might have latency in terms of seconds or something for that. If we want a faster response time, we can send our data up to the fog, do our processing in the fog, and then send it back down to the edge again and make decisions based on that a whole lot faster. The other is processing power. Now, often our edge devices don't have lots of processing power associated with them. And so they can't do things, on the whole, some can, but a lot can't, like image processing or video processing, for example. But our fog devices, which we have not billions of, but millions of, we typically have a bit more computational power there. And so what we can do in the fog is have a whole lot of data coming up from our edge devices, do the processing in the fog, and then send it back down again. Also, we can upload data into the cloud from the fog. Now, in terms of communicating that data, there's a whole lot of classical network topologies that can be used. Things like ring networks and line networks and tree networks and buses. These don't tend to be used as much in IoT. The ones that tend to be more commonly used within IoT are our mesh and our star networks. Our star, particularly where we've got a gateway, where we've got a whole lot of devices connecting to a gateway, and that central node is connecting it to, is maybe in the fog or connecting it to the cloud. Or a mesh where we might have several devices that are sharing information between each other, but they don't necessarily need to be fully connected to each other. And then they can share that to the cloud somehow. Now, getting back to IoT conceptually, we understand that IoT isn't a single technology that's just been introduced. It's not one single thing that's new, that's revolutionary. It's a whole combination of different technologies. And some of those combinations have been around for a long time. For example, connecting things to the internet isn't a new thing. We've been doing it with computers for decades, but the concept of combining all these microcontrollers and embed systems and everything else that goes around IoT, and you can see a whole lot of spokes of this wheel here, are quite new. And so our origin of IoT in terms of just connecting things isn't new, but all these things that sit around it, everything from, well, we have heaps of data with IoT, so we need to start virtualizing that data. We need to do data analysis with that data. We need to do big data applications and machine learning and things like that. Somehow we need to get that data, which requires our sensors, which requires our real-time operating systems and embedded systems to actually get that data. We need to transfer that data from our embedded systems to the internet, and we use wireless technology and various networking technology to do that. We have software that we need to control these things, and also security layers on these things to make sure our data is not compromised. Now we'll briefly look at how IoT looks from an enterprise system. And basically we see the diagram at the top where we have an asset being something that we want to monitor or control. And that asset is connected to some sort of an IoT device. So that IoT device might have some actuators with it. It might have some sensors with it. It gets data and interfaces somehow with that asset, and then sends that onto the network. From the network, we have to route that around and get towards our IoT platform and eventually our IoT application. And in doing so, we can monitor and control those assets remotely from a mobile phone, for example, or from a computer, or we can have software that's written that controls a whole series of those assets based on information that's been provided, or aggregates that data and gives us aggregated data that we can make decisions based on. Now we'll turn our attention to architecture for a moment. And I should say that there's not just one generally accepted IoT architecture that here's the architecture. In networking topologies, there's a couple, and they're fairly fixed, like the OSI 7 layer and things like that. But here we have a number of different layers. There's 3-layer models, there's 5-layer models, there's 7-layer models. We're going to do a 6-layer model. And the 6-layer model covers the asset layer, the device layer, the communications layer, the service management layer, the application layer, and then finally the business layer that sits on top of them. Now, some of those names will have different names for those that are interchangeably used as well. So we'll go into a little bit of detail on each of those. Firstly, though, at the bottom, we have our asset layer. And realistically, the asset layer isn't really part of the IoT system. It's what the IoT system sits on top of and is trying to either measure or control. So the asset layer might be things like a robot or a manufacturing process or a building or a bridge or an aeroplane or people even, or animals, all sorts of things that we're trying to get information from the real world. It could also be something that's a bit more virtual or procedural in nature. For example, our asset layer for a logistics company might be trying to work out what's the best way we can route our trucks to get from point A to point B, for example. And we might have inputs into that in terms of some time of day optimization for avoiding school zones and things like that. From traffic intensity, measuring traffic through a region, looking at roadworks and avoiding roadworks, looking at weather conditions. There might be some areas that are flooded that we don't want to go into. And so there's a whole lot of different areas around our asset layer that our IoT system will actually want to measure and hopefully eventually control as well. Now, sitting above our asset layer is our device layer. And our device layer, which is also sometimes called the perception layer, is the layer that interfaces with the asset layer with those sensors and actuators that I talked about previously. So it's trying to measure things and gather data on those assets and then send that data on through our networking that we'll cover in a moment. Now, that could be a bunch of sensors, anything from chemical sensors to accelerometers to temperature or environmental sensors, all the different sensors that we've talked about thus far in our course. But it could be other things as well. For example, if we've got a whole lot of bags going through an airport, all our luggage and things like that, they might put RFID tags on them or barcodes and things on them. And so our sensing systems might use RFID, for example, to track things going through an airport or through a logistics system. Or they might be using positioning technology like GPS to basically report on the position in 3 dimensions of an object. Where is that object actually gone? Now, sitting above that device layer is our communications layer. And in our communications layer, sometimes called the data transmission layer or the network layer, what we're getting is that data, rather than just being in a device layer and gathering data and it not going anywhere, we actually want that data. And so we'll transmit that data somehow, probably eventually to the cloud. And in doing so, we've got a whole bunch of different protocols that are being used. Everything from Ethernet and TCP/IP, which is standard internet protocols that are used. MQTT, which is a commonly used messaging protocol. CAN buses, which are commonly used in vehicles, or Profibus or Modbus or Ethercat, which are commonly used for industrial equipment. So there's a whole bunch of different protocols to allow that data that's being collected to be transmitted and shared within our system. We then have our service management layer, which is sometimes called our middleware layer that sits on top of that. And there's a whole lot of routine tasks that are done when our data is received that we might need to do things with it. And this is that middleware layer that covers that. We might need to strip various parts of that data off. We might need to do things like performing checksums and things and making sure that our data integrity is there. We might need to do a whole lot of processing on our data to maybe remove erroneous data or some filtering that's required. Aggregating huge amounts of data and working out how we store that data is done at this spot. We're doing some analysis on that data, for example, doing some machine learning or some neural networks and things like that. And some abstraction of that data, putting it in a form that other software that's going to be visualizing that data or aggregating that data later on can actually understand and use. Then we have our application layer. So our users don't want to see, for example, taking an example around location-based data, our users don't want to look at their phone and say, where is Mary? And they see just a whole lot of GPS coordinates. Those GPS coordinates aren't all that useful to them. Now, they could take those GPS coordinates and put them in Google Maps or something like that and find out where she is, but it would actually be a whole lot more useful if that data is in a format that the user can understand and use and action things based on. And so whether it be the web portals or the apps or software that's being used on the website or on people's computers, is putting it in a form that's most useful for the user to actually gain information that they need from it. Likewise, if we're measuring someone's heart rate, for example, we want what their heart rate actually is and maybe if there's something wrong with it, not every single data point about what their blood pressure is looking like at various times through that heart rate cycle. Now, finally, we have the business layer where we aggregate a whole lot of our data and a whole lot of our things from our previous layers to look at business models and look at flowcharts and graphs and look at a high level of how this is all looking. Our business layer allows enterprises to make decisions, much wider and larger decisions based on the aggregation of a whole lot of data. And so here above you see a whole lot of summaries of some of the things that happen in each of those layers, from our device or perception layer through our network, our middleware layer, our application layer, and our business layer as well. Now, going back to our original definition, we said that each of these devices should have a unique address of some kind or another. And typically the addresses that things use that connect to the internet is an IP address, an internet protocol address. And traditionally we've used an IP version 4. It's been around for decades now. And IP version 4, we had a 32-bit address that was assigned to everything. And that 32-bit address looked something like maybe 1.0.5.10 or whatever it happened to be. It was a series of 4 octets or groups of 8 binary digits that allow us to encode our address. And with 32 bits, we can have sufficient addresses for 4.3 billion addresses. Now, when IP4 first came out, 4 odd billion addresses seemed like a huge number. But now, with billions of new IoT devices, it doesn't seem like such a big number anymore. And so for the last couple of decades, we've been introducing IP version 6. Now, rather than having a 32-bit address for each device, now we've got a 128-bit address for each device, which allows for a huge number of devices. In fact, 100 times the number of atoms in the Earth is the number of addresses that we have for our IPv6. So we probably won't be running out of addresses anytime soon. Having said that, the internet currently supports IPv4 and v6, and so there's been a gradual changeover from IPv4 services to IPv6 services over time.